Alright class, next chapter we're going to talk about kinetics. Now before I talk about kinetics, I want to give you a fun example. Carbon graphite going to carbon diamond, okay? The delta H of this reaction is 1.88 kilojoules. If you remember that if there's a positive delta H, that means the reaction is endothermic, and endothermic reactions are not favored because you have to put in energy in order for this reaction to happen. Okay, so delta H of reaction is positive. This reaction is not really favored. Now, delta G, if we haven't talked about this yet, we will talk about this later. Now, delta G gives energy. Basically, gives energy is going to tell you if the reaction is going to happen or not happen at room temperature. And here, the Gibbs energy is positive. If the Gibbs energy is positive, that means the reaction is not going to happen at room temperature. Okay, so this reaction, carbon graphite going to carbon diamond, is not really favored. So we're going to have no reaction. This is not going to happen at room temperature. No reaction, which is kind of sad. Otherwise, we could take graphite and make diamond from it. Now, how about if we take diamond and then it goes to graphite? Basically, this is the reaction on top flipped. Now, what I want you to do, tell me what would be the delta H of this reaction. I can hear you, but tell me anyway. What would be the delta H of this reaction? Well, this reaction is the reaction on top flip. When you flip the reaction, what do you do to the delta H sign? You notice, if you flip the reaction, the sign for delta H is also going to be flipped. So this would be negative 1.88 kilojoules. Okay, now, negative delta H, that's an exothermic reaction. We like the exothermic reaction because not only they don't require energy, they're going to release energy into the surrounding. Okay, so this is very interesting. Thermodynamics is going to say that this reaction is going to happen. Thermodynamics is going to say, yes, this reaction is going to happen. Is going to say, yes, this reaction is going to happen. Isn't that interesting? I had a friend who was convincing his girlfriend, who was showing his girlfriend the scientific fact. He said, I should not buy you diamond because if I buy you a diamond, over time, diamond is going to turn into graphite. As you can see, this is the delta H of this reaction. Thermodynamically, this reaction is favored and diamond will turn into graphite. This reaction is a yes. It will go. Okay. Did he have a point? He was trying to take the easy way out. He had a point, except his girlfriend was even smarter than that. And she said, correct. Thermodynamically, this reaction will go. But you also have to care about kinetics. What does the kinetics will tell you? Thermodynamics tell you this reaction will go, but what it doesn't tell you how fast this reaction will go. Kinetics is going to say that this reaction is going to take 1,000,000 years to happen. So kinetically, this reaction is a no. So just because thermodynamics is going to tell me a reaction is going to happen, it doesn't tell me how fast it's going to happen. Kinetics is going to tell me if kinetically this reaction is favored, will it happen fast enough? And in this case, this is going to take 1,000,000 years for it to happen. So this is not going to happen. You can buy a diamond. It's going to be okay. Don't use that excuse to not buy a diamond. All right, so far so good. So that was an intro into kinetics. Kinetics, what is kinetics? Thermodynamics will tell you if the reaction is going to happen. Kinetics is going to tell you how fast this reaction is going to happen. Rate of chemical reaction. Kinetics is looking at the rate of chemical reaction, looking at the speed of chemical reaction to see if the reaction is going to happen, how fast the reaction is going to happen. Now, it also gives us some idea about the mechanism of the reaction. And we'll talk about mechanism later. Okay, so what's kinetics again? Kinetics is the speed of chemical reaction, how fast chemical reaction is going to happen. Just because thermodynamics tells us a reaction is going to happen, it doesn't mean it's going to happen fast. The speed of the chemical reaction, the rate of the chemical reaction, that has to do with kinetics. Also, kinetics gives us some idea about the mechanism of the reaction. And we're going to go over that in a little bit. All right. Now, the next thing we're going to talk about before we really get into the equation, we want to talk about what affects kinetics of a reaction. What is going to affect the kinetics, the rate of a reaction? Number one, temperature. And you probably already knew that, right? Temperature, of course, is going to affect the kinetics of the reaction, how fast the reaction goes. And you already know that if you raise the temperature, what's going to happen to the reaction? If you raise the temperature, the reaction will go faster, right? By the way, RXN means reaction. So temperature goes up, reaction will happen faster. You already knew that. So temperature will affect kinetics. What else is going to affect kinetics? Another variable that is going to affect kinetics is the physical state. Okay, what does that mean? Let's say I have a magnesium strip versus magnesium dust. Which one do you think is going to have a faster reaction if it's reacting with something? The strip or the dust? Hopefully you're telling me that the dust is going to have a faster reaction because it has a larger surface area. It has a larger surface area, so it's going to react faster. So physical state also matter. Number 3, pressure. Pressure matters. When you change the pressure, you change the kinetics of a reaction. You change the speed of the reaction. Number 4, concentration. Concentration really matters. Concentration really matters. And let's talk about this one for a little bit. What do you think is going to happen if I increase the concentration? What do you think will happen to the rate? If I increase the concentration, the rate will go up. It's going to happen faster. Why is that? Here's why. When you increase the concentration, they can find each other faster because you have more of it, right? You can find each other much faster. So you can watch it faster and the reaction is going to happen faster because you have more of it, higher concentration, they can find each other faster. Okay. Now, number 5. Number 5 is catalysis. Number 5 is catalysis. Okay. Now, what does a catalyst do? Catalyst would speed up the reaction. Catalyst would speed up the reaction, right? Example of catalyst, probably you know it from your biology classes. An example of catalyst would be enzyme, right? In biology class, enzymes are catalysts. They're going to speed up the reaction. So far, so good? Okay. Now, what I do want to do, I want to have a side note and talk about catalyst. I want to talk about catalyst because catalyst is one of those things when I ask my students to explain it, they always give me the textbook definition. This is why I don't like textbook. They say, yeah, catalyst speed up the reaction. But what is a catalyst? How does it speed up a reaction? So I want to take a minute to actually explain to you what a catalyst is. And you can show off your knowledge to your friend and impress them. So let's go over. Okay, this is a round bottom flask. It doesn't look like a round bottom flask, but it is. My drawings sometimes are questionable. So, this is not a pumpkin. This is a round bottom flask. So, a catalyst. let's go over what is a catalyst. Enzyme is a catalyst. In chemistry, usually transition metals are catalyst. Okay. Now let's go over what is a catalyst. What does a catalyst do exactly? How does it speed up a reaction? Now let's say I have A plus B going to C. Okay. And I'm going to use platinum. What platinum is a catalyst. Platinum is a transition metal, is catalyst. Also, a little fun fact, platinum is white gold. When you buy white gold, it's actually not gold, it's platinum. But that's okay, it's even more expensive. So, A plus B going to C. And this is platinum, is my catalyst. Okay, now what that means is, in this reaction over here, I have A and I have A and B reagents floating around. So far so good. Okay. And I'm going to have my platinum right here. Now, usually the way that I teach this to my Chem 30A class, I say that catalyst is like Match.com for atoms. It's like an online dating. It's a Match.com for atoms. It creates a surface. It creates a place for atoms to come together and to react. So that's the best way I can explain it. It's like Match.com for reagents, for atoms and compounds. So here I have A and B floating in the solution. So here I have my platinum, which is my catalyst. So catalyst is going to create a surface where A and B can come to the surface and they can find each other and they can react. So it makes it easier for A and B to find each other. They're going to come to the surface and they're going to find each other and they're going to react. So it creates a surface for these reagents, for these atoms to come together and to react. That's how it speeds up the reaction. So kind of like Match.com for atoms is a pretty good description. I kind of like that. So far so good. So hopefully now you know exactly what a catalyst is. So it creates a surface that the reagents can come on here, they can find each other and they can react. The same thing online dating does, right? It creates a place that people can go there and they can find each other. All right, now let's go to the next part. So now that you know what's kinetics, speed of the reaction, how fast the reaction happens, and now that you know what affects the kinetics of the reaction, the next thing we're going to do is how to measure rate. How to measure rate. Okay? There are two ways we can measure rate. What you can do, you can look at the change in concentration of reactants or products. So you can look at the change in concentration of reactants, or you can look at the change in concentration of products. So far so good. Okay. Now I'm going to put up something for you. Okay, there we go. So check this out. Here I have A going to B. Okay. At time 0, I have 6A. At time 22nd, I have 4A, now I have 2B, because at time 0 there's no product. After that, more products is forming. At time T is time 42nd, now I have 3A and I have 3B. So as the time goes by, more and more products are going to form. So hopefully that gives you kind of a visual picture that for reaction A going to B, there are two ways we can measure the rate. We can measure it based on how many of the A is going to go away, or we can measure it based on how many of the B is going to appear. You can follow me so far? So, for the reaction. So for the reaction A going to B, there are two ways. There are two ways. That was not ways. There are two ways to measure rate. There are two ways to measure rate, okay? So the first one, there are two ways to measure it. But what I can do, I can measure the speed at which reactants disappear. Or what I can do, I can measure the speed at which products are going to appear, are going to form. Okay? So far so good. I'm going slow because kinetics can be tricky. I want to make sure you understand every step before we move on. So there's two ways to look at it, as you can kind of see in this picture. I can look at how many of A is going to go away, or I can look at how many B is going to be forming. Now, which one is the better way? The better way of doing it is this one over here. This is a better way, okay? Because at the beginning, we mostly just have the reactant, right? Early on, we only have reactant. So this is a better way to do it because early on, mostly and sometimes entirely, we only have the reactant. So it's better to look at the rate that the reactants are disappear. So far so good? All right. So far so good again, because again at the beginning you really don't have any product, and even at the beginning of the reaction you still have mainly the reactant. So it's easier to look at the speed at which reactants disappear. Now, what we're gonna do, we're going to measure the rate of reaction in terms of change in concentration. Again, I'm going slow. I'm writing everything down because I want to make sure you have a really good grasp on the basics before we get a little harder. In terms of change in concentration per unit time. And that's really key. So the way we're going to measure the rate, we're going to look at the change in concentration per unit time. We're good so far? Okay. Now, if you remember, sometimes for concentration, we show concentration by having a bracket. So right here, when I have A in a bracket, that means that's a concentration of A. And in chemistry, what we love molarity as a concentration, right? Yes, we love molarity. So when you see bracket, what are you going to be thinking about? Every time you see bracket, you're going to be thinking about molarity. So far, so good. So we're going to do this together. So we measure the rate of the reaction in terms of change in concentration per unit time. Yeah? So rate is going to equal minus delta A over delta T. Okay? Now, don't forget, let me make sure you're on the same page as me, what we were talking about. The reaction we were just talking about last page was A going to B, right? And it's easier to look at the change in concentration for the reactant, yeah? Okay. So the rate is going to be minus, and I'll talk about it in a second. Why is minus? The delta concentration of A over the delta T. And again, what does delta means? You know that. Delta means change, right? Delta means change. So change in a concentration of A over change of time, because the rate is change in concentration over per unit time. So far, so good. Now, so change in concentration of A over change in time. Now the last thing to kind of talk about is that what is going on here? Why is this minus? Why is this minus? Now remember, we said we can look at the concentration of A disappearing or the concentration of B appearing, forming, right? So because reactant disappear, because my reactant and A is a reactant, right? Reactant, they disappear over time. What that means is the concentration of A is going to go down. We have a minus here. Because the reactant are going to disappear, the concentration is going to go down over time. So far, so good? Okay. So this is rate in terms of A, the reactant disappearing. Now we can also write rate in terms of the products forming, right? And in that case, it would be the change of concentration of B over delta T. Now, here, how come I didn't put a minus? Because B is forming. B is a product, is appearing over time. Versus A was a reactant, was disappearing over time. Okay, so we can write a rate expression for the products, or we can write a rate expression for the reactant. And I'm going to just write this down. So these are rate expressions. Rate expressions. So far so good. In terms of, we can write it for the reactant or we can write it for the product. All right, beautiful. Now, let me put up an actual equation. So far so good. N2O5 going to NO2 plus O2. What I want you to do, good old days, balance this reaction for me. Balance this reaction for me. If you balance this reaction for me, it would be 2 over here, 4 over here, and that is 1. Okay? Now, here is what I want you to pay attention to. What are these coefficients? This will be 1. I'm just going to write down 1 for now. What are these coefficients? What do coefficients mean? Think about, I know we've talked about coefficients and balancing reactions. It seems like years ago. So think back 2 months ago when we've talked about this. What do coefficients mean? Coefficients means hashtag mole ratio. Coefficients means mole ratio. That's what they mean. Coefficients are the mole ratio, right? Now, if you look at this equation, if you look at this reaction, here's what these coefficients are telling me. They're telling me that for every 1 mole of O2 that forms, 4 times as many moles of NO2 is going to form. In the meantime, 2 times of N2O5 is going to disappear. You guys follow that? Okay, so for every 1 mole of O2 that appears, 4 times many moles of NO2 is going to form. And in the meantime, 2 times of that NO2O5 is going to disappear. So, the change in concentration is going to be inversely proportional to the mole ratio. The change in concentration is going to be proportional to the mole ratio, which is the stoichiometric proportion. All right, so far so good. Okay. Now, I'm going to write a rate expression for this. So the mole ratios matter. This is what I get a hashtag mole ratio. They're always going to come back. Now, let's talk about this rate expression. I'm going to say rate equals. I can write a rate expression for any of them, right? I'm going to write a rate expression for the reactant first. So my reactant is N2O5, and we said that the rate expression would be the change of concentration over the change of time. So it would be the concentration of the change of concentration of N2O5 over delta T. You guys agree with that? Okay. Now, I'm not done. And we've talked about that because I'm writing the rate for the reactant disappear. What do I need to put over here? I can almost hear you. I need to put a minus over there. Okay? But also, the mole ratios matter. The stoichiometric proportions matter. And we said that the change in concentration is inversely proportional to the mole ratio. So over here, I will put a minus 1 over 2. I will put a minus 1 over 2. And again, the minus is going to remind us that the reactants are disappearing. All right. Now, I can also write the rate expression for the products, right? Let's write it for NO2. You write it first before you look at mine. So it would be the delta, the change of concentration of NO2 over the delta T. And again, the product are forming, so it's going to be a positive. Now again, remember, the mole ratios really matter. So what's the mole ratio for? So they're inversely proportional, so 1 over 4 equal. Okay, now we have another product, and that is O2. So I can write the rate expression for any of those. So it would be the change of concentration of O2 over delta T. And the mole ratio is just 1. 1 over 1 is just 1. Yeah? Okay. Very nice job. Now, the way to kind of look at it, these ones are basically the mole ratio, right? The stoichiometric proportion, those are basically the mole ratio. There's one more thing I want to talk about before I end the first kinetics lecture. Again, I'm going slow. I'm going to keep going slow because I want you to really grasp the basics. Once you know the basics, you're going to have an easy time when we get a little bit fancier. So, rate, which is going to be, as we've just talked about, the change in concentration over unit per time. So the change in concentration over time has always a unit of molarity per second or molarity per time. But this is the unit you are going to be seeing all the time. So let's summarize this one more time. I know I'm repeating myself. Just one more time. Let's do this. So we are going to measure the rate of the reaction in terms of change in concentration per unit time, right? So we could use the reactant or we could use the product, but in both cases it would be the change in concentration over time. So delta molarity over the delta T. So the unit for rate is molarity per second. It could be different time unit, but the molarity is key. It's going to be molarity per second, and that is going to be my rate. Sounds good? All right, beautiful, nice job. We survived kinetics lecture 1. Next time we're going to continue with this.